So I'm actually talking about topological defects in graphene. So I have to be quick. There is plenty of experimental evidence showing that graphene is actually not exactly a two-dimensional sheet of carbon, but it's corrugated. So it develops these waves. So what we became interested in is whether distribution of topological defects could be a model for this kind of experimental observations. So this corrugated graphene both on substrates and the freestanding is also observed to be corrugated. So there's plenty of experimental evidence for that. The idea is the following. If you have both Professor Ijima and Professor Rogério showed images of topological defects in graphite and graphene. The idea was that if we had, if we have a distribution of topological defects, and you can notice that they are isolated in the sense that, contrary to what Rogério, for example, showed, the 5-fold and 7-fold rings are all surrounded by hexagons. What that makes is that they like to be corrugated in this sense. So the pentagons would develop some curvature, and also the heptagons. So we would have a corrugated graphene that corrugation would be induced by this distribution of topological defects. So we decided to study the properties. This is a computational and theoretical work. Properties of systems like this. And there's several that we can build. I don't have time to explain, but the interesting observation is that depending on the density and also on the distribution of topological defects, they can actually be metals. They can have the same behavior as graphene in the sense that it's a zero-gap semiconductor here. And they can also be a finite gap semiconductor. So that depends on the nature of the distribution of defects. So we built a lot of these topological networks, and we observed this very diverse electronic behavior going from metal to semiconductors. I don't have time to explain this, but we have 3 different families of topological defect networks here. The structures that I show here, they're all in the plane, so these are planar structures. But if you allow those corrugations that I showed here to develop, then the energy of the system is reduced. And there's also the impact, the effect of the corrugation on the electronic structure. And there's a general tendency of reducing the density of states at the Fermi level, which goes hand in hand with the fact that the energy tends to reduce by if you allow the corrugation to develop. So in this one you have, this would be the electronic structure. So this is a density of state plot. Showing the density of states at the Fermi level. So you have a lower density of states at the Fermi level. This would be the planar form, and this is the corrugated form. And in this one, you actually open a gap at the Fermi level by developing the corrugations here. And we also addressed the formation energy of these structures. And it turns out I'm giving here the best example, which is this one. So this would be the planar form, and this is the corrugated form. It turns out that this system, if we compute the formation energy with respect to a perfect graphene sheet of this structure, it's only it's a little less than 0.1 eV per atom. To give you an idea, a fullerene has an energy with respect to graphene of 0.4 eV per atom. So from the energetic point of view, this would be a very favorable structure. The problem is, how can you form this? That's the problem. So far, this is really a theoretical study because there's no those experimental slides that I showed in the beginning. The analysis done by the experimental groups, they don't believe that there's any evidence of topological corrugation. But in corrugated graphene. But there's a very recent work that's very recent, last month, I think, in Nature, where people are actually building these ribbons of graphene with control at the molecular level. So this would be the precursor And they actually start to add together molecules like, so this is a carbon ring here, this is a Br, bromine. And this hydrogen also here, and they can actually control this on top of a substrate in order to form very narrow graphene ribbons here. So we believe that, for example, if you have a precursor with topological defects in it, you could actually try to build a distribution of topological defects, but that's only a suggestion. Now, one thing that really correlates with the experimental evidence in our work is this, that there's actually a tendency of clustering of topological defects. Rogério showed one picture where you have two five-fold rings and I believe seven-fold rings in a hexagon. And this one, what people did was to try to produce graphene from reduction of 2 minutes. It's okay. Graphene, GO. What is GO? Graphite oxide, yeah. Graphite oxide. By trying to remove some of the oxygen in some process, they managed to build structures like this. So in the region where you see only hexagons, you have pure graphene. Now, in these regions here, that are marked here, you have, they believe you have functionalized, so that there's still oxygens and hydroxyl groups on this, on top of the carbon atoms in this area here. So you see also evidence of some isolated five-fold and seven-fold rings here. And what we did was to, okay, so this is functionalized graphene, these areas here. So what we did was to functionalize our topological networks with hydroxyl and also with hydrogen. And by applying strain, so imagine this would be one of those examples of the topological networks. And we added hydrogen, for example, on top of each carbon atom here. It turns out that if we apply strain on this system, it actually segregates, so the topological defects they cluster together. And it turns out that the counting of topological defects and hexagons here, so this is a final structure of adding hydrogens and applying strain on this structure here. It goes into this by relaxation. Okay, this is this compares very well with the experimental images in this work, experimental work of reduction of graphene oxides. And there's also, this is another one, this is from another one of those examples of topological networks with hydrogen. Again, we applied strain, and you see, you form these are now octagons and pentagons. They form this sort of basic unit here. And this has been recently observed. This was actually created by choice. So they have domains of graphene with different orientations here, and the junction of these domains is this, what they call this nanowire of graphene, exactly with this unit. So this is another example where our results compare very favorably with stuff that has been observed experimentally. So let me end here. Okay. So this, what we conclude is that strain favor clustering, and the functionalization leads to reduction of the energies. I didn't show you any results, but this is what we have plenty of results to conclude that, and barriers for the transformation that leads to the topological defect formation. And this is all agreed with that experimental evidence in which they claim that areas with topological defect clustering remain with functional groups. Okay, so let me end here. Thank you.